Okay, so we're going to start our chapter 15 by looking at what we call iterated integrals. So recall from Calculus 1, if you have a function of one variable, so maybe this is some function y equal to f of x, well, one thing we could do is we could differentiate this function with respect to the variable x. And then another thing that we could do is we could integrate this function with respect to the variable x. But recall that when we're integrating, what we're actually finding is, and this would be if the function is above the x-axis, is geometrically we're looking at an area where the f of x would be, say, a height, and the d of x, that would be a base. So essentially what we're doing when we integrate is we're summing, which is why there's a big S, we're summing up the areas of rectangles with a height of f of x and a base of dx. So dx is just a very, very small base, right? Essentially getting closer and closer to 0. So let's look at what happens when we have iterated or double integrals. Well, now we're dealing with a function of two variables, and that would be our z function equal to some function with the independent variables x and y. And recall from your previous calculus class that when we take the derivative of a function of two or more variables, you have to do the derivatives separately. So you have a choice. You can look at what's called a partial derivative of the function with respect to either the variable x, or you can look at a partial derivative with respect to the variable y. Well, the same thing's going to happen when you integrate a function of two variables. Okay? But now we're going up a dimension. We're adding a variable, so we're adding a dimension. So this is no longer an area. This is a volume, where we have the height of our object as being the value of the function. So this is your z value. It'll give you a height. But now we have this area in the xy plane. So this would be an area. So there's an area in the xy plane, and then this area is going to have some height, which will make this volume. So let's kind of look at sketches of that idea. In single variable calculus, let's say that you have this red curve, that's our function. If we want to approximate the area of this region, what we do, our strategy is to break it down into rectangles, and we add up the area of those rectangles. So remember, this is just an approximation where this distance is going to be some delta x. I'll just call it delta x1 since it's the first subinterval. So if we were actually going to, instead of using an approximation, if we're actually going to accurately tell what this area is, remember what we're doing is we're taking the limit as your delta x's, and here I'm going to use sub k, so it's for all these distances. We're taking the limit as that distance gets closer and closer to 0. And that gives us that Riemann sum from our first to our nth interval of our function, and I'll use x sub k times delta x sub k. And once we take the limit, once we make that distance get very, very small, right, then we can accurately fill up the area with these really skinny rectangles. And instead of having an approximation of the area, we have an actual area. So that's what we would call our integral. Okay? From some, in this case, the x sub 0 could be like our a value. and the x sub 6, I'll call that my b value of our function with these dx's, these differentials, these very, very small base or width. Same idea when you're looking at three-dimensional space. You're going to have some region in the xy plane that will give you an area. So there's going to be a delta x, a distance in the direction of the x-axis, and a delta y, a distance in the direction of the y-axis. When you multiply those two lengths, what you get is you get this area. And this would be our delta A. So for that area, each area, if you look at this second diagram, each area is going to correspond to some z values on our surface z. And that will give us a volume. So what we're going to do is we're going to add up all those volumes, and that would approximate the volume that we create. But it's just an approximation. Until we take the limit, or if we look at these delta A's, until we take those delta A sub k's and we let them get smaller and smaller, approaching 0, then it's still just an approximation. That goes back to our Riemann sum. So here's the Riemann sum definition for an iterated or double integral. Okay? So in the definition, what they're saying is this area, delta A sub k, is going to approach 0. But they just use delta as a shorthand instead of writing delta A sub k, which gives us our double integral, and that's usually a volume. Let's go ahead and compute one of these double integrals. So I've already set this up for you. In example 1, we want to evaluate the iterated or double integral. What you do is you work from the inside out. So notice here that the innermost integral has a dx, which tells me I'm going to integrate with respect to x first. Now you could do this integral off to the side, or you could simply do what your textbook does and compute the integral without doing it as side work. So for example, I would keep the outer integral from 0 to 1. On the inner integral, since we're integrating with respect to x, what we do is we treat the y squared as if it were a constant. Think about substituting the number 3 in there. So the antiderivative for the x portion would be x squared over 2. And then the antiderivative for the y squared would be x times y squared. So this becomes x squared over 2 plus x times y squared. Okay? And we're evaluating this from 0 to 2. But I still have the dy on the outside. So again, you can always do that inner portion off to the side and then just substitute it into your integral later. But I'll keep it all together as your textbook does. Looking at that innermost integral, x squared over 2 plus x y squared, we're putting in 2 for x, so that becomes 4 over 2, or 2 plus 2y squared, minus, putting in 0 for x, this becomes 0 plus 0. So I really don't need that. And this is that whole inner integral. So the 0 plus 0, that's just gone. And now I'm going to evaluate the outer integral from 0 to 1 of 2 plus 2y squared with respect to y. So order does matter here. That's going to be 2y plus 2y to the third over 3. And then we're evaluating from 0 to 1. So putting in 1, I have 2 plus 2/3. And then the 0 would just be minus 0. So putting that together, what do we get? 8/3? And that's how you compute your double or iterated integrals. Sorry. We're going to look at the simplest case, and that would be our theorem 15.1. We're going to look at double integrals on a rectangular region. So when we talk about a rectangular region, that just means in the xy plane, that region R that we're looking at is going to be a rectangle, which means the limits of integration are going to be constant real numbers. And now that's what we had in our previous example. So now in example 2, what we're going to do, and what's really nice about these rectangular regions, if you look at the formula, is when you take your dA, which remember that would be dx times dy, you can do it in either order. You could do x first, or you could do y first. So remember, you're working from the inside out. Now, sometimes in advanced physics classes, they actually work double or even triple integrals from the outside in, but in mathematics, we always work inside out. Because the limits of integration are constant real numbers, the order that we integrate does not matter. But this again is the simplest case. We're going to look at more complicated cases later on. But we have the double integral over our region R of 3x squared sine y dA. And we know it's a rectangular region because I look at my limits of integration for x and y, and they're constant real numbers. So this tells me when I set up my integral, I can set it up in any order I want. So I'm looking at my x and I'm looking at my y. And both are easy to integrate. 3x squared becomes 3x to the third over 3, so I'm noticing, the 3's will cancel. Maybe I'll do the x's first and then I'll worry about the sine y later. So I'm going to choose to set up my integral so that my y is last, which would mean that remember y is going from 0 to pi over 2. So I'm going to have the y last. I'm going to put my x's first, that's 1 to 2. 3x squared sine y. So I'm going to do x first and then I'm going to do y. But it doesn't matter. You could have done it the other way. When I integrate with respect to x, remember the sine y is going to remain constant. So that's going to be 3x cubed over 3. And the 3 should cancel, so this integral on the outside is going to remain the same. This is going to be 3x cubed over 3, which becomes x to the third. The sine y remains because it's constant, and I'm integrating here from 1 to 2. So again, the outside stays the same. The integration here would be 8 sine y minus sine y. And it's a dy. You could put parentheses or brackets around this, but it's not necessary once I've evaluated on the inside. And that just becomes 7 sine y. So now I have to integrate with respect to y. Antiderivative of sine is negative cosine. This becomes negative 7 cosine of y. I'm evaluating this from 0 to pi over 2. So cosine of pi over 2 is 0. This becomes 0 minus, and then cosine of 0 is 1, so minus a negative 7. And I have positive 7 as my answer. All right, so we're just going to do a bunch of examples. In example 3, we evaluate this double integral over the region R. Again, notice that my region R is rectangular because my x and my y have constant real number limits of integration, which again is the simplest type of iterated integral. Now, looking at this integrand, I have y over x squared plus 1. Right away, I see that if I treat the x squared as a constant and I integrate with respect to y first, I know that the integral of y is simply y squared over 2. If I was going to treat y as if it were a constant and integrate with respect to in the denominator x squared plus 1, I don't know if you remember, this would be like an inverse tangent. Some ways are shorter than others. But since it seems to me that integrating with respect to y is fairly simple, when I set up my integral, I'm going to choose to do x last. So my x goes from 0 to the square root of 3. I'm going to integrate with respect to y first because that seems easier to me. And then I'll just treat the x squared plus 1 in the denominator as if it were a constant. So it's a dy dx. Now you didn't have to do it in that order, that's just how I chose to do this. So now again, on the innermost integral, x squared plus 1, I'm ignoring that. Again, just sticking a random number, 3. How would you integrate y over 3? It's y squared over 2 times whatever is in that denominator. So it's the same thing. This is going to be y squared over 2 times whatever that denominator is. And I'm evaluating this 0 to 2. Again, you can do that innermost integral first off to the side if you choose, and then plug it in later if you choose. Remember, we're putting 2 in for the y. We really don't care about the x squared plus 1 because we're integrating with respect to y. So if you put in 2 in for the y squared over 2, then that's just going to give you 2 over x squared plus 1. So again, we still have the 0 to the square root of 3. That's going to give us 2 over x squared plus 1. And then if you put in 0 for the y, the term just becomes 0, so that's it. Okay, so you can choose to pull that 2 out from the numerator. And if you do recall, that 1 over x squared plus 1, that would be, antiderivative would be the tangent inverse. And now you didn't have to pull the 2 out. You could have left it in there. This becomes 2 on the outside. This is tangent inverse of x. And we're going to evaluate this 0 to the square root of 3. The tangent inverse of the square root of 3, I think that's pi over 3. I'll write it out. So this is 2 times tangent inverse of the square root of 3 minus 2 times tangent inverse of 0. Now tangent inverse of 0 is 0, so that term is 0. Tangent inverse of square root of 3 should be pi over 3. So this becomes 2 times pi over 3. Or 2 pi over 3. So let's look at another example. An example for the language has changed a little bit. Previously I just gave you integrals and you had to evaluate. But this says find the volume of the solid bounded by the surface z equal to 2 plus 3x squared y over the region R that's given. So since you're supposed to be finding a volume, we're going to use a double integral. And when it says a solid bounded by the surface, this is your function f of x, y. That's your integrand. And the region that you're integrating with respect to happens to be rectangular because your x values are constant and your y values are constant. This volume that we're supposed to find is simply the double integral of, now we have to decide the order in which we're going to integrate. So it really doesn't matter if you integrate with respect to x or y. Now I see if I'm integrating with respect to x, I get 3x cubed over 3 and the 3's cancel. So maybe I'll just do the usual dx dy. If y is on the outside, then the outer limits would be from 1 to 2. The inner limits would be the negative 1 to 2 for the x. The integrand is 2 plus 3x squared y. And I'm going to go dx dy. So this volume, outside integral remains the same. The inside integral here is going to be 2x plus x to the third over 3, so just, or 3x to the third over 3, so the 3's cancel, y is constant because I'm integrating with respect to x. And then I'm going to evaluate this from negative 1 to 2. Okay, so plugging in 2, this is the integral from 1 to 2. I have 4 plus 8y minus, plug in negative 1, it becomes negative 2 minus y. Simplifying, it looks like 6 plus 9y. And then we integrate with respect to y. So integrating with respect to y, we get 6y plus 9y squared over 2. Evaluated from 1 to 2. Alright, so it looks like it's going to be 12 plus 18 minus 6 plus 9 over 2. Okay, so plugging all this in a calculator and choosing fraction, it looks like I get 39 over 2. Alright, let's look at one last example. I know these are a lot of examples, but it's a nice way to review integration. Since Calc 3, most of the problems are basically derivatives. We want to evaluate this double integral. So look at the numerator. It's x e to the x, and the denominator is y. Now the region is rectangular. We have constant limits of integration for x and y. So I have to choose. If I integrate with respect to x first, then I'm going to kind of ignore that y. And I'm looking at x times e to the x. Recall that you would have to use integration by parts for that. So let's say that I just hold x e to the x constant, and I look at the 1 over y. So the 1 over y would be natural log. I don't feel like doing integration by parts just yet. I'll probably still have to do the integration by parts. I think I want to do y first. When I set up this integral, I'm going to set it up with x from 0 to 1 on the outside. And then I'm going to use the 1 to 2 for the y. X e to the x over y. I'm going to integrate with respect to y first, and then x. Something that I want to bring to your attention is that since this is essentially x e to the x times 1 over y, and remember I'm treating the x e to the x as if it were a constant, like a number, like say 3. That on this particular problem, I am going to pull that x e to the x out, treat it as if it were a constant, and then just integrate the integral from 1 to 2 of 1 over y dy. Just because I don't want to keep writing it in there, it kind of gets in my way. This will be the integral from 0 to 1 of x e to the x. Now this integral, 1 over y, that's natural log. So this becomes a natural log of absolute value, remember? To keep those absolute values on until you look at your limits of integration. And this is from 1 to 2. That becomes the natural log of 2 minus the natural log of 1, and the natural log of 1 is 0. So that whole integral is just the natural log of 2, and we have the integral from 0 to 1 of x e to the x times natural log of 2 dx. So recall the natural log of 2 is just a number, it's a constant. I'm going to bring it out into the front of this integral, and then do integration by parts on x e to the x dx. When I do the integration by parts, it's a good time to review this. I'm going to, so remember that would be uv minus the integral of v du. So I'm going to let u equal the x, because I know when I take the derivative, I get du equal to dx. And I'm going to let the dv portion be equal to e to the x dx. When I integrate, I get v equal to e to the x. So we set up our integral as u times v minus the integral of v du. The natural log of 2 is still on the outside, so I'm going to use brackets to write out my integration by parts. It becomes x e to the x minus the integral of e to the x dx. And I'm going to evaluate this from 0 to 1, which is the natural log of 2 x e to the x minus antiderivative of e to the x is simply e to the x. Plugging in 1 for x, I get again the natural log of 2 on the outside. This just becomes e minus e minus, putting in 0 for x, 0 minus 1. So this is natural log of 2 times 1, and the answer is simply natural log of 2. Enough with the different types of integration. I'm going to look at a special case. Here, this is not in your textbook, and this refers back to our previous example. Remember when I kind of pulled the x e to the x out, and I ignored it because it was constant, and I could factor it out because I had this product, x e to the x times 1 over y? Well, in the case, and this is only where you have constant limits of integration, in the case where you could separate your integrand into 2 functions, one with respect to x, one with respect to y, and it has to be a product. So if you can do that, then you could simply split it up into 2 integrals. You just have to remember that the region that you're integrating with respect to has to be a rectangular region. So a, b, c, d are constant real numbers. We're going to go back to example 3. Remember when I looked at example 3 and I decided that I was going to integrate with respect to y first because that just seemed simpler at the time? Well, let's say that you're looking at this problem, and the previous one as well, previous example, and you're not sure which would be the shortest way to go, because some ways could be shorter than others. Well, if you have the case where you can take your integrand and you could separate it into a product, and this integrand, oops, I don't want it to be that thick, This integrand I can separate into a product. Notice that this is the same as y times 1 over x squared plus 1. So here I was able to write this as a product where all the y's are in one, all the x's are on the other side of my product. So if you can separate your x's and your y's this way, what you can also do is separate your integrals this way as well, and look at, say, the integral. Since I have y written first and y was from 0 to 2, I could write this as y dy times, and then I can look at the integral with respect to x. That was 0 square root of 3, and the x was 1 over x squared plus 1. So again, the caution is you have to be able to separate it into one function with only y's, one function with only x's, and it has to be constant limits of integration. You cannot have a variable in your limits of integration. So if that is the case, again, this is not in your textbook, then you could separate it into two different integrals, so the order that you choose really doesn't matter. If we look at this first integral, with y, that's just y squared over 2 evaluated from 0 to 2. And then the second integral, this is tangent inverse of x. We're evaluating this from 0 to square root of 3. So I'm going to go ahead and evaluate them separately and then multiply them. So the first one is going to be 2 times the tangent inverse ended up being 2 times, or pi over 3, sorry. So this becomes 2 times pi over 3, which is 2 pi over 3. And that's exactly what we got when we did example 3 the other way, by going from the inside out. Again, not in your book, it's just a very special case. Sometimes, again, if you're confused on which to start with and you could separate in this way, well, maybe just do them separately. The last thing we're going to look at in this section is from Calculus 1. It's the average value of a function. Recall when we look at the average value of a function, we use this f bar. And to find the average value of a function, all you're doing is you're taking the integral and you're dividing it by the length of the interval that you're integrating with respect to. So if we take that formula and we apply it to double integrals, we can also find the average value of a function as well. So if you have a double integral, you would be dividing it not by the length of an integral, you'd be dividing it by the area of the region in the xy plane. In example 7, it says, find the average value of the function. The function is two variables, x and y. So that tells me if I want to find the average value of the function, I'm going to use a double integral, but I have to divide it by the area of the region. So the area of this region, and it's a rectangular region, so the area here is simply the length of the x times the length of the y, because it's a rectangle, right? An area of a rectangle is length times width. So if you look at your x values, they go from 0 to pi. So the length is pi times. When you look at the y values, they go from 0 to pi over 2. So the length along the y is pi over 2. Multiplying these, I get pi squared over 2. So we don't want to approximate. We want to keep all our values exact. And now when I find the average value, or f bar, that's going to be equal to 1 over pi squared over 2 becomes 2 over pi squared. And my integral is sine of x cosine of y. It doesn't matter to me which one I do first. Let's see, the antiderivative of cosine is sine. Antiderivative of sine is negative cosine. Also notice that I can separate this because I get sine of x times cosine of y. So I could use that previous property that I introduced and separate this into two separate integrals, one with respect to x, one with respect to y. I think I'm going to do y first, and I'm going to keep them one inside the other. So my x values go from 0 to pi. And the reason why I'm going to do the y first is because I know that when I find the antiderivative of cosine, it's positive. I don't like having a negative when I do my first integral. So I'm going to do y, which would be from 0 to pi over 2. And this is sine of x cosine of y. I'm going to do dy dx. Again, you don't have to do it in that order. That's just the order I choose to do it in. And now, since my sine of x is being treated as a constant, I am going to pull it out and then integrate from 0 to pi over 2 cosine of y dy. I'm going to do this piece first and then x second. Notice I would not pull that sine of x out to the front of both integrals because it's sine of x. I still have to integrate with respect to x, so it still has to stay on the inside. It can't go where the 2 over pi squared is. But I can pull it out of the integral with respect to y. So cosine just becomes sine of y evaluated 0 to pi over 2. And that's sine of pi over 2 minus sine of 0, which is just 1. And I'm not going to bother to write that. Since it's just 1, then I'm going to integrate from 0 to pi. Sine of x times 1 is simply sine of x. And the integral of sine of x is negative cosine. Oops, I forgot the square on my pi. So this is 2 over pi squared times negative cosine of x evaluated from 0 to pi. Negative cosine of pi is 1 minus cosine of 0 is 1. So it's going to be 2 over pi squared 1 minus a negative 1, which is simply 2. The final answer is going to be 4 over pi squared. And that's it for this section.